what are we going to do? Well, we're going to look at some nice constructions using the method of initial segments. Our constructions so far have been of the form, or many of them have been of the form, do some computable stuff, and then after you've done some computable stuff, you enumerate something in, and then you do some more computable stuff, and you enumerate something more in. And so what happens is that, of course, you're kind of determining initial segments of your set, but the initial segments keep changing because you enumerate some more stuff in. So the method of initial segments really just says, okay, we're going to construct a sequence of finite sequences of zeros and ones, and the final object we care about is the union of all of those, and sigma n is an initial segment of sigma n plus 1. So what you're thinking, or what you should be thinking, is that sigma n is an approximation to the characteristic function of the object we're trying to construct. Right? In general, this will be the characteristic function of some set A we're trying to construct. So these are approximations to these characteristic functions, and as you go along, you get better and better approximations, right? A bigger finite sequence of zeros and ones is a better approximation for this characteristic function, and so maybe the biggest difference with what we've done before is, as soon as you settle on a sigma n in your construction, you're not going to change it. So sigma n is a finite initial segment. There might be lots of numbers in this initial segment for which sigma n says 0, so it's not in there. At no point later on are you going to decide to change this initial segment. You only extend initial segments. This is the method. Okay, we're done. We can go on. Now we need to see how this works out in practice. How it works out in practice? Well, of course, if you were able to do this computably, then your f would be computable, and therefore you'd have a computable set. And computable sets are not usually the most interesting. So going from sigma n to sigma n plus 1 is usually a little more complicated. Sometimes you don't care how complicated it is at all, you just want to end up with a certain set A. Other times you do want to get some restriction. And now if I want my set A to be Turing reducible to some set B, what I have to do is to make these decisions be computably. And as soon as I can make these decisions be computably, then my set A will be Turing reducible to B. Okay. So what are we going to do first of all? Well, first of all, we have this picture. Here are all Turing degrees. Here is 0 jump. Here is 0. The tilde underneath to indicate our boldface. These are the degrees. And so we want to see what this whole structure looks like, and in particular we care a lot about these sets here in between. Even more particularly, we care about the subset of these sets, which are the CE sets. And so, with everything we know so far, it would be absolutely amazing, but not contradictory, to presume that the whole collection of Turing degrees is like a linear order. We haven't gotten any incomparable sets yet. So that's going to be our first theorem, that there exists A and B which are incomparable. Right? Turing incomparable. And we're going to do this a little better because we're going to do it below zero jump, so that yes, there are incomparable degrees, but there already are incomparable degrees in the part we care more about than the other part. So this is what we're going to do. Okay, using initial segments, okay, sigma approximates S. So we're going to construct approximation sigma S, which approximates A, tau S, which approximates B. And we're going to make these approximations computable in zero jump. Right? We get to ask holding questions along the way. And then we want to make them incomparable. Well, how do you make them incomparable? You just satisfy the requirements. RE, which says that the eth Turing functional does not compute A using B. And SE, which says that the eth Turing functional does not compute B when it uses A as an oracle. So I think pretty clearly, if you satisfy all RE and all SE, then you have incompatible degrees. That's exactly what it means to be incompatible. Incomparable. Comparable. Incompatible means everything's compatible, right? There is a minimal degree, so incomparable. So this is what we have to do. Well, that's easy enough. Notice that by the same observation, this automatically means that A and B are not computable. Of course, if you are incomparable, neither one of them could be computable, but right, there are all Turing functionals which ignore their oracle. So it's kind of explicitly included as well. Okay, so what do we do? Well, we start, of course, not unpredictably from nothing. Take the initial segments to consist of nothing. And now I am at stage in my construction, at stage S plus 1, which is oh, we're doing A and B separately. I was going to do in one step in the stage work on RE and SE, but the construction as the book chose it to do, which I thought does right work on SE at stage 2e plus 1, and then work on RE at stage 2e plus 2, right? So you're working on the R requirements on the even stages and on the S requirements in the odd stages. It's just some bookkeeping device. I don't actually care. Right? At stage S plus 1 equal to E minus 1. I forget, right? I already did 0, so E minus 1 or E plus 1, make sure I still get all E. I think it's minus 1. Plus 1. Right, so at this stage, I'm going to take care of both RE and SE. And how do I take care of this? Well, I know I already have sigma S and tau S constructed. These are finite initial segments, which I don't get to change around. And now I want to make sure that if I'm computing from B, I will not compute A. Well, how do you do this? First of all, you can choose any n which is not in the domain of sigma S. So this is saying this is an n, a natural number, for which the initial segment, which is approximating A, doesn't tell you whether it's in or out. Right? This n is one you can still make up your mind. And you can choose the least one. Right? If you want to be specific about it, we just choose the length of the segment. That's the first one, which is not in the domain, and you have a place where you can still make up your mind. Now what is it we want? We want to set this equal to 1 or 0, exactly opposite from the value that's computed from B. Right, so we look at phi E, right, B of n. We clearly can't do this because we don't have B, but this is what we're thinking about. And what we want to do is that if this happens to converge, well, then it converges either to 0 or to a non-zero value. If it converges to 0, we can set this to 1. If it converges to a non-zero value, we can set this to 0. So whatever the value, like a characteristic function, you have two options for the value. You can always choose it different for this given value. But of course you don't have this value. But what you do have is that tau s is going to be an initial segment of B. So what are we looking for? We're looking for a way to determine B so that this computation converges. So what we're looking for is, does there exist a tau which is an extension of our current approximation tau s, such that from tau this converges. And now for complete explicitness I should put in here, does there exist an s such that it converges in s steps? Because now we clearly have existential quantifiers over something computable. So this is a question that zero jump can decide. And so either the answer is yes, there exists such a tau, then we can choose tau s plus 1 to be the least such tau. Right? If there exists such a tau, otherwise we let tau s plus 1 just be the same. Right? We let zero jump decide if we can make this computation converge. If it converges, then we choose something which makes it converge. If it never converges, then we choose. Right? You could choose an arbitrary extension if you want to make progress at every step, but we don't care about making progress at every step. Anyway, so what this means is, after we've gone to Ts plus 1, either this value is determined, no, after we've gone to Ts plus 1, this value is determined either to diverge or to converge to a specific value. And then we just choose sigma s plus 1 at n to be not equal to that value. Right? And not equal to that value means you choose 0. If it diverges, choose 0. If it converges, choose an opposite value. Right? And then we switch our gears and we do the same thing, but now in reverse. We look for the least value, which is not in tau s, that we haven't determined yet here, and see whether we can extend our current approximation for A to make this converge, and again choose it differently. Maybe it's better to separate out the two stages after all. Because I just said tau s plus 1, which kind of indicates that I do it. But of course, the situation is symmetric, so there is nothing new going on. And I think I already argued that it works. I've convinced myself already that it works, so I haven't convinced you yet, and you should stop me now. But right, this is clearly the right thing to search for. Zero jump allows you to do that, and then you choose the other one just different. And this way you can work it out. Because the whole construction is zero jump computable, we get that both of these things are computable in zero jump. And they're clearly incomparable because they satisfy all these requirements. And now of course, you look at this and you see, maybe I should have done this separately, right? I indicated this sort of general idea before. You come up with the requirements. After you have the requirements, you figure out how would you satisfy one requirement. And that's kind of the basic module, how you do one requirement. And that's exactly the analysis I gave here. So now that you have this basic module, you can say, okay, what else can I do with it? What else you can do with it is, for instance, construct 3 sets which are all incomparable pairwise. You just need a minimal amount of extra bookkeeping, but you can one after the other take care of these kind of incompatibility requirements, and then you get 3 incomparable sets. But you can also do countably many incomparable sets, because as you're going around, in the end rotation of doing all these things, you take care of the first n requirements for the first n sets. And you cannot take care of the first requirement for all sets and then go to the second requirement for all sets, because after you've done infinitely many steps, you have these things. Then this becomes infinite. So you have to do a little more bookkeeping, but right? We have a fairly flexible method here for creating incomparable objects.
So there's no way to know in this construction whether A and B are strictly less than 0 jump?
Yes, there is. Not because of the construction, but because of the result of the construction. If one of them, right, they are both below 0 jump and they're incomparable. If one of them happens to be equal to 0 jump, then you would get the comparability out of it. Yes.
So we don't really need the full force of the 0 jump oracle, do we? I mean,
you need to be able to decide these questions.
Yeah.
It looks pretty full to me. Right? We're going to look at every computation, and for every computation, we are asking a sigma 1 question.
I mean, if they're both strictly below 0 jump, right? So, I mean, there's something.
Yeah, you only need their join.
Yeah.
But their join might be 0 jump.
Oh, right.
But really, like,
but of course, the join you only have after effects, right?
You can explicitly construct A, explicitly construct B, then take their join and just say.
Absolutely. No, after the fact, it might be that both of them are simpler, and you can do all sorts of things. But before the fact, it's not clear to me how at least this construction could give you something simpler. And the join might be 0 jump, so even that construction might not give you anything simpler.
Well, that itself seems to be a somewhat interesting property that.
I can actually make the join 0 jump.
But can you make it not 0 jump?
Yeah.
Oh, yes. Can I make it not 0? No, I'd have to think about that.
Yeah, I mean, that's an interesting property itself, that any two incomparable elements between 0 and 0 jump have to join to 0 jump.
Oh, I don't think that's true. That sounds awfully wrong.
Elements are like dual atoms.
Wait, because do I immediately know the right theorems to show that that doesn't happen?
Well, couldn't you try and do the same construction, except for now you've got A, B, and C, and you just make sure A can't be computed from B or C?
Yes, of course. Yes, take your incomparable triple, then the join of A and B. Well,
I'm saying you modify the construction, so it can't
modify the construction so that also the join of A and B is not computable from C, and then you get it, right? You can really do awfully general embeddings using similar ideas like this. I'm not going to give you the details, but this part of the degrees is countably universal. Am I lying now? No, I'm pretty sure that any countable poset embeds into this. I hope that's true. Anyway, I'm not going to prove
Can we
it.
prove that between any two Turing degrees there's another Turing degree?
Between any two CE Turing degrees, there's another Turing degree. So this is probably going to be the crowning result of this course. It's an infinite injury priority argument to show that between any two CE degrees you can find another one strictly in between. This is the Sachs density theorem. It's the density theorem, but I'm not quite sure about it.
So
I'm
that'll
pretty sure.
allow you to embed like Q and
Yeah. But it's more general than that, right? There's linear
Yeah.
orders.
I was just thinking of something that would break.
Yeah. Okay. So as observed just a second ago, or maybe not observed, remarked, right? The CE degrees are dense according to this Sachs density theorem. So this sheds some doubt on the question of whether there could be a minimal degree, a degree below which all degrees which are strictly below it are computable. Now that clearly exists. A non-computable degree, all degrees which strictly below it are computable. Now that doubt is not entirely justified, but at least it's a good idea to step back for a moment and to do something which we can do fairly easily at this point, which is the construction of a minimal pair. Degrees A and B greater than 0 are a minimal pair if for every degree C such that C is less than A and C is less than B, we have that C is the degree of the computable set. So how do you do this? Well, you need to write down the right requirements, and this is people use this enough that I do want to say something about it. I am not myself that excited about it, but there is the so-called Posner trick, which says that if A is not equal to B, it's clearly in a minimal pair A and B, right? The degrees should be different degrees, so different set. Then if it is the case that for some I and j, the thing computed from A by the machine I and the thing computed by j from the machine B are equal, then it is the case that there exists one machine E such that phi A of I is equal to phi E of A is equal to phi E of B. And so what you see here is that as long as you don't do anything silly by accidentally constructing the same set twice, if you have conditions of the form, if the functionals compute something the same, something happens, then you could presume that you're looking at the same functional in both cases. So it avoids a minimal amount of bookkeeping. The proof is of course easy. A and B are different, so there is a natural number n which is in one, not in the other. So phi of E, the first thing it does is ask the oracle the question, is n in there or not? After the oracle gives the answer, you know whether you're dealing with A or B, and then you continue computing as I or as j. So it's a very simple idea, which in many cases reduces your bookkeeping just a little bit, but people like it. So
I don't know. I mean, I have a.
it looks like too clever to me. Okay. So then the theorem. There exists a minimal pair of degrees, and it turns out that, again, like before, what we cared about initially was do there exist incomparable things, and then we managed to get them below zero jump. Here the same thing happens. There exists a minimal pair below zero jump.
Do there exist maximal pairs in the reverse order?
Yeah, because you said to join, you could join to be zero.
Okay,
So yeah,
okay, got it.
this is
I did not get the question, but if you're happy with the answer, then we're good.
Just look at the image up close to zero jump and look at the join.
Okay, do there exist things which join up to zero jump? So was that your question?
not stated that way.
Not stated that way, yeah. And Matt showed me that it is the same thing.
Okay. Good. If you're happy, I'm happy. That's my goal in life, right? At least for this 2 to 3 every afternoon.
Very depressing if it wasn't.
Okay. Below zero jump. Oh, and before you ask, from that, you can get them strictly below. Does it automatically follow? I thought for a moment it automatically followed. If one of them is equal to zero jump, then the other one would be a minimal degree, but we haven't proven that you can't have that.
Well, if they meet down to the bottom, can you just take anything else?
Oh, of course, because these things are going to not be zero. So if one of them is zero jump, then the meat of the two is the one. But what is the picture? What we want is to get these A and B like this, below zero jump, such that whatever is below both of them is equal to zero. Well, if A or B was zero jump, then the other one would be below both of them and not equal to zero. So, yes. Constructing them less than or equal to zero jump makes them strictly less than zero jump. Right? If B were up there, then A would be less than or equal to A, and A would be less than or equal to B, but also A is non-zero, so it wasn't the minimal pair.
Your definition really don't have equalities.
Huh?
Yeah, that'll still work if A is in between zero.
I don't know why I'm paying a lot of attention to this anyway. I care about there being a minimal pair. What do I care about zero jump, right? This is the picture anyway. Okay. Easy enough. What do we want? Well, first of all, right? They should not be zero. How are you not zero? If you satisfy that you're not equal to phi e and b is also not equal to phi e. And now you should look at this and immediately realize, okay, we're doing a construction, right? We're computing initial segments using zero jump. So using zero jump, on any input, it's easy to decide if phi e holds or not. And then, just like before, decide if phi e holds or not. If it holds, compute its value and choose A to be different at that place. Right? So the strategy for these things is going to be like we did before, but easier. The other requirement, using wonderful Posner trick, if phi e A is equal to phi e b, right? If there is something computed by both A and B, well, this should be total, right? If A and B jointly compute something, then it should be the case that it is computable. How do we say this? Then phi e A is computable, right? You didn't need an oracle in the first place. Then there exists an I such that phi e A is equal to phi I. More explicitly. Okay, so again we construct these sigma s approximating A, we construct tau s approximating B, and we do the bookkeeping in such a way that we work, say, on PE in the even stages and NE on the odd stages. At the even stage, you know exactly what to do. Pick the least point not yet in sigma s, or pick any point not yet in sigma s. Decide if phi e holds at that position. If it doesn't, then choose arbitrary. If it does, then choose the value of sigma different from the conversed value. Then do the same thing for tau, the other way around. So these two steps take care of PE. And then we go to the next step. Now we take care of NE. Well, how do you take care of NE? Well, you have to wonder. I have initial segments, or I have an initial segment approximating A, and I have an initial segment approximating B. Now, how can I win for this requirement? Well, there's two ways to win. One is, I have sigma s and tau s. I can look for extensions of sigma s and tau s such that I compute different values. Anywhere. Find a place where they compute different values. If I can do this, find a place where they compute different values, then I win because the hypothesis is false. Right? What does this mean? I look for, does there exist a sigma and a tau and an x such that sigma s is an initial segment of sigma, tau s is an initial segment of tau, and phi e of sigma of x is not equal to phi tau of e at x. Let's make it complete. Comma s, both computed in s steps. And then you notice that the question is exactly of the right form. Here I have a computable part over which I only existentially quantify. So this is a question that zero jump can answer for me. If zero jump says, yes, there are such sigma and tau, then I extend sigma s to sigma and tau s to tau, and I've won. So then the only difficulty is, what if zero jump tells me there are no such sigma and tau? Right? Well, if there are no such sigma and tau, one of two things can happen. Either phi e is a computation that's just under no choice of oracle converges, or there is a location for which phi e under no choice of oracle converges at that location, in which case we win because it's not total. Or, for every choice of location, we could find one where it converges, but whichever one we find, it always converges to the same value. But then we're done, because then it's computable. right? If for every possible sigma and tau where this value converges, you always get the same value, then you no longer need to know which sigma or tau you picked as initial segments of A and B, because whichever segment you picked, if it happened to be total, it was that value. And therefore, it becomes computable. You disagree violently?
Did we ever specify that sigmas and taus would be different? I mean, could they be initial segments in the same set?
Okay, so
That should be easy to fix.
sigma 0 at 0 is 0 and tau 0 at 0 is 1. In all other cases I've said, I wrote it over there. Here I didn't even talk about initial conditions, but your initial conditions you can pick however you want. And in this case, I'm sure you can argue that there are computations where you can get different values, so they would eventually become different anyway, but you might as well choose them different from the start so you don't have to worry about it. Everybody happy with that? It's kind of nice. We're looking, can we make them different? If we can make them different, we win. If you can't make them different, the thing that's computed is either partial or computable. Okay. Oh, there's a lot more quantifiers here. Oh, he named these two different values. I don't know why you would want to do that. Okay, so those were two constructions by initial segments, computing from zero jump. Now, some of you have done some set theory and have heard of this notion of forcing, and you might notice that if you're talking about forcing, you very much use the same ideas as you use in this initial explanation I said. Right? In forcing, you're looking for an object, the generic, which you want to have certain special properties. And what does your process consist of, the process you force with? Well, it consists of approximations to the generic. And even if you do co-enforcing, then it exists exactly of the approximations we were using here. That's kind of similar. And then you also notice something, or you could now retroactively look at these proofs and notice that right, going from sigma s to sigma s plus 1 was satisfying an additional requirement. And what is the additional requirement? Well, showing that you can always extend appropriately amounts to showing that the set of sigma satisfying these requirements is dense. It's a little more than dense, right? Because you don't just want to have that sigma s has an extension, you want to be able to find this extension. But it does correspond to the idea as it is in forcing, where you go from one approximation to a better approximation by jumping into a dense set. Because we're doing effective stuff, you need to jump a little more effectively. So, Now we'll introduce some more forcing terminology to have a good basis for these kind of words. So first of all, of course, what I want is to talk about CE sets of finite sequences of zeros and ones, and this just, right, our CE sets are sets of natural numbers, and by some appropriate coding, any natural number represents a finite sequence of zeros and ones. What do I care? Binary expansions, but you need to be a little more careful with binary expansions because these things can end in finite sequences of zeros, and these can't. So you need to set it up right. But in the beginning of the course, we talked long enough about coding that you can figure out something that'll work here, some nice way of coding. So this means that we can now look at arbitrary CE sets, and when we so please, consider them to be a CE set of finite sequences of zeros and ones. Or a subset of the collection of finite sequences of zeros and ones is CE if the corresponding set of codes is a CE set in our proper sense of CE. Okay, so then we say F, which is a real, an infinite sequence of zeros and ones, it forces WE if what happens if either there exists an initial segment sigma of F such that sigma is in WE, or for every rho extension of sigma, rho is not in WE. So what does it mean to force WE? Well, to force WE means that some finite bit of information from F decides whether the initial segment is in there or whether there is no such initial segment. Right? And now you would rightly wonder, where is the dense set? Right? Because this doesn't seem very dense. The fact that you can stay out of it by all these things. Of course, dense sets you can have infinite things which stay out of it, but this is a cone which stays out of the set. So clearly WE is not dense. But what is dense? Well, the set of things, the set of extensions of things in WE, a union the set of things that don't have extensions in WE. Right? That union is dense. And so what do we have here? Our WE is just, say, the set of those conditions which positively determine the outcome for a particular question. And then this is the set that negatively determines. So it's kind of half of a dense set. Maybe I don't want to be quoted on that. But you can see that there is a dense set here, even though it's not WE. Now we say F is generic if, well, of course, if you are one of these people who knows about set theory, then you know what it means to be generic. Generic means intersect all dense sets. Now, intersecting all dense sets is really too much for us to ask, because we're doing computability theory. So that's why instead of generic, we define one generic, and that means that F forces all WE. Right? F decides all. F has initial segments which decide. For every WE, there is an initial segment which decides this WE. The one, of course, indicates exactly the sigma oneness of all the sets that we we work well with respect. Okay, I'll finish by making this last definition, and then we can make a running start on Monday. Requirement JE is there exists a sigma, an initial segment of A. Well, sigma is an initial segment of the characteristic function of A, which we must be right like this because we're lazy, such that it holds for all extensions do not hold. So what is this? This is exactly deciding the jump in exactly the same way as I suggested. This is deciding set WE. Right? You're in where you could never get in. You converge, or there's no extension which converges. And you notice that this is something which we did a little bit ago. Or not unrelated to what we did. We didn't really decide a jump yet, but we were looking for can we make it converge somewhere, then we do something, or is it always diverging? So on Monday, the first thing we'll do is see that being one generic is equivalent with satisfying all jump criteria.